Assalamualaikum and a very good day to everyone. So today let's continue our topic in electrostatic, which is regarding on the electric flux density, which we have discussed in previous lecture, but we will continue with other example in this lecture. Alright, so we're gonna look again into the electric flux density. So I hope by now you already remember the symbol and the applications of the Gauss law, okay, where D is equals to what? Epsilon naught E, and the Gauss law, the formula is given as closed integration surface of D dot ds is equals to Q enclosed. Alright. Okay, so now let's look into the learning overview is same as before. We're going to look about the electric flux density, and we're going to also look about the applications of Gauss law. But in today's lecture, we're going to look specifically on the surface charge. In previous example, we have discussed about the line charge, but in this example, we will discuss about the surface charge. Okay. So we have discussed these questions, or we have discussed this example in our previous lecture, right? Where we are able to prove that although by using different law, okay, the answer that we obtain is same, yeah, no matter you are using Coulomb's law or Gauss law. Alright. We haven't discussed what is the Gaussian surface. What is the imaginary surface? Before I did mention to you guys where you need to draw the imaginary surface. So what is this imaginary surface is all about? So this imaginary surface is also known as Gaussian surface. Okay, it is also known as a Gaussian surface. And that surface must be a closed surface. What I mean by closed surface, it must be a closed structure. Okay, for example like this, it must be a closed structure. So this is the imaginary surface or the Gaussian surface. It must be a closed structure. It must be a closed surface. And that particular surface must be in a symmetrical surface. Okay, it must be either cylindrical, spherical, or any other surface, but the structure, the shape must be a symmetrical surface. And the electric flux must be directed normal or in parallel with the surface. So the electric flux here must be directed normal or parallel with the surface. Okay, so for example, let's look in our previous example that we have discussed in previous lecture before. Okay, so for this line charge, the appropriate imaginary surface is a cylindrical. So we know the electric flux here is in our direction, right? In this direction. So for surface number 1, we can see that the electric flux is normal or parallel. It is parallel with the surface number 1, right? But for surface number 2, the one that is around the cylindrical, the electric flux is normal to this, okay, normal to this surface, right? To this surface, it is normal to the surface. And for surface number 3, which is located at the bottom, the electric flux is parallel with the surface, yeah. So the electric flux must be either in directed normal or parallel with the surface of this imaginary surface ataupun Gaussian surface, right? So that is a Gaussian surface or imaginary surface that we have been discussed before. Okay. So now, how to decide which surface, which imaginary surface that we must draw, okay, if we want to use this Gauss law, alright? So these are the summary, the respective Gaussian surface that that suits with this kind of electric source. Okay, for example, when you have a point charge, okay, okay, the Gaussian surface, the appropriate Gaussian surface will gonna be the spherical surface. Okay, and if for infinite line charge, the Gaussian surface or the imaginary surface, yeah, Okay, remember ya, Gaussian or imaginary. Okay, we're going to be the cylindrical surface. For the sphere uniform, okay, sphere uniform charge, we're going to be spherical surface. Sphere uniform rho v, we're going to be the spherical surface. Cylinder of uniform rho s, we're going to be the cylindrical surface. And cylindrical of uniform rho v will be the cylindrical surface. So these are the summary in case that you guys are not sure what kind of imaginary surface that we want to draw. Okay, I hope this is going to be helpful to you guys. Yeah. Okay, now let's look the Gauss law for the surface charge. So surface charge, it is represented as rho s. Okay, so remember to use the Gauss law, it is strictly only for the infinite area of surface charge. Okay, infinite area of surface charge, remember that. Okay, so our aim now, we want to find, okay, our aim now, so this is the infinite surface charge. Let's assume that it has a rho s here. So our aim now, we want to find electric field. Electric field, which is E, yeah. But now we want to use the Gauss law, okay, instead of Coulomb's law. So the first step will be, we must to draw the imaginary surface or Gaussian surface. Okay, I hope you can read my handwriting. Okay, it's very bad here, but I hope it is readable. Okay, Gaussian surface. Okay, so what is the appropriate Gaussian surface for this structure? Can you guys guess? So it will be the cylindrical. Okay, it's gonna be the cylindrical surface. So let's assume that this cylindrical have radius r. Okay, it has a radius r and it has the height of L. Okay, and make sure that this surface, okay, this imaginary surface must enclose the electric source. Must enclose, meaning that the electric source now is, which is now a surface, must be inside the imaginary. So in this case, it is inside the imaginary. Okay, so this is going to be on the z direction. Okay, all right. So we need to apply. Okay, now so let's proceed. Let's solve this one. So we know to use the Gauss law. The first of all, remember the formula. It is d dot ds is equals to q enclosed. So let's solve separately. So this is our left hand side and this is our right hand side. So let's look at the left hand side. We have how many surfaces now at the left hand side? For your ds, going to be one on the top, second one, which one, the surround the cylindrical, and the third one, we're going to be at the bottom of the cylindrical. So if we can solve, d dot ds, we're going to be the summation of first surface, d dot ds, plus second surface, d dot ds, plus the third surface, d dot ds. Okay, plus the third surface, d dot ds. So for the first surface, let's decide your d first. Yeah, your d in which direction? Your flux here in which direction? So your flux, the one that is produced by this electric source, which is the surface charge now. So it can be exist in a positive z direction, and also it can be exist in a negative z direction, right? Negative z direction and positive z direction. Okay, so these are where the directions of the flux that can be exist for this surface charge. Alright, so once we know that, let's look into surface number 1. Okay, d dot ds. For surface number 1, we're going to be so for surface number 1, your d will going to be in z direction, since that it is located on the top, yeah. So your ds also, so your ds also gonna be in, your ds also gonna be in positive z direction. Okay, for surface number 2, your d will gonna be remain in z direction. Okay, z in d in z direction. Okay, d in z direction. Okay, d in z direction. Another bad handwriting. Okay, d in z direction, and your ds will gonna be in which direction? Your ds should be same as previously what we have discussed. Your ds should be in r direction. Okay, it's not detectable. So your ds will be in r direction, right? So for surface number 3, your d will gonna be in negative z direction. Okay, for surface number 3, because it is located at down, so it's gonna be negative z direction, and your ds will gonna be in negative z direction. And if we solve this, okay, your d will gonna be in, it's gonna be dz. Okay, this part, yeah, it will become d on z. Okay, and the ds will gonna be the area for this one, yeah, for this whole top surface. So let's give the whole top surface the area as s, the area as s. Okay, so plus, okay, plus dz on s as well. On s as well. Okay, so we will get 2 dz, 2 dz s. Okay, alright, so for the right hand side now, for the right hand side now, so for the right hand side, the q enclosed we're gonna be integrations of rho s ds. It's very difficult, yeah, to write on this. I don't know, perhaps I need a new one, yeah. Okay, the ds. All right, so your ds will gonna be the area. The ds will gonna be the area of this, right? The area of this charge. So the area will same as the one that is located on the top, the imaginary area, right? So it's gonna be rho s s. So if we can make it equality, both of it, left hand side and right hand side, it's gonna be 2 dz s equals to rho s s. Okay, so if we can simplify, this s can be cancelled out, so your dz will be rho s over 2. And same as before, to change it or to convert it into vector. So your d will gonna, astaghfirullahalazim, your in terms of vector, it's gonna be rho s over 2. It will be rho s over 2 on z direction. Okay, rho s over 2 on z direction, and to make it as E, electric field intensity, so it will be as rho s over 2 epsilon naught, right, on z direction. So this is what we have obtained by using Coulomb's law before. Okay, and don't forget the unit. Okay, don't forget to write the unit. Okay, so we can see the one that we are able to obtain by using Coulomb's law is same as what we have able to obtain by using the Gauss law, where to make it normal, z is actually the normal surface. Z is actually the normal surface. If you still remember, inside our Coulomb's law, we said for the infinite structure, it's gonna be rho s over 2 epsilon naught on normal unit vector. Right? Okay, so you can see now, by using any law, as long as it is an infinite area, okay, you are able to obtain the same result. Okay.